All right, Chemistry 3101. We left off last class. We'd finished up chapter 18, and we're going to take a look at these practice problems now. And so we'll start with the first one. We've got a benzene ring, and then we've got this secondary alkyl halide, and we're treating that with also with aluminum chloride. And so we can see that there would be a rearrangement in this, wouldn't there, right? Because if you formed a secondary carbocation, and I'll just maybe scribble it up here in blue, right? If you were to form a secondary, that didn't work, secondary carbocation on this guy, right? You know that there's a proton here that could undergo a shift, and then that would give us this carbocation, which would be more stable, right? We'd go from a secondary to a tertiary carbocation. And so the major product is going to be the one that results from the rearrangement. So what's going to happen first is that the chlorine is going to react with the aluminum chloride, and I could just put in the lone pairs here. So it's going to act as a Lewis base. Of course, the aluminum chloride is a Lewis acid. And then once that reaction happens, we form our intermediate. So we form this complex where we have the chlorine attached to the aluminum. So the aluminum is going to have a negative charge, and our chlorine has a positive charge. But again, after this breaks apart, we end up with the secondary carbocation here. And of course, that can go produce a hydride shift, which will give us the tertiary carbocation. And I've already drawn this once, right? But it gives us this. And then when that reacts with the aromatic ring, you end up forming the sigma complex, and then you do a proton transfer in the end. And so the compound that you're going to get from the reaction is going to have an attachment between one of the carbons on the aromatic ring and this carbon here. All right. And so what is that going to look like? Well, let me just back up here. It's going to look like this. We're going to have our 5-membered ring like that, and then we have our ethyl group coming off of this. So that would be the major product. Would you get some of the attachment, would you get some of this as a minor product? And that's not part of the question. But the answer is, I suppose so. You would get some of this product as well. So we could put here minor for this one, and then we could put major for this guy. All right. There we go. So that's number one. And of course, don't hesitate to stop me if you have any questions at any point. And I'll try to ask you some questions along the way. So for the second question, it says provide the structures of the intermediate products and the final product in the following reaction sequence. So could anybody tell me what the name of the product is for A? What's the product A? So we're treating the benzene with aluminum chloride, which is our Lewis acid, and methyl chloride. Can anybody name the compound? Yeah, you form toluene, right? Thanks, Tiana. So we're going to end up taking our aromatic ring, treating that with methyl chloride and aluminum chloride, and we end up forming toluene. And once we have toluene, we can do a halogenation reaction with that. So the next one is with chlorine and heat. And I don't know if I covered this one in detail with you or not, but this would affect the benzylic chlorination if you just treat it with chlorine and heat it up enough. So don't worry about that reaction for the quiz so much, but you end up doing a benzylic chlorination so that you end up making benzyl chloride in this case. And of course, that can react in a Friedel-Crafts. And so the first reaction was a Friedel-Crafts. This reaction is a benzylic chlorination. And we'll actually look at the mechanism of that reaction in chapter 10. And then the last reaction is a Friedel-Crafts with a primary alkyl halide that cannot undergo any kind of rearrangement. And so we treat that with benzene and AlCl3. Yeah, there we go. We're just going to end up adding the aromatic ring on that carbon. So we have 1, 2, and there you go. So there's our final product, just like that. Okay, good. Next one. Oh man, they're just loving these rearrangements here. Predict the major product for the following reaction. So in the first reaction, right, you would end up with this primary carbocation technically, which would undergo a rearrangement, wouldn't it? Right, to give you a tertiary carbocation. So this is going to be your electrophile, right? So you're going to end up making, once you have your aluminum chloride, you're going to end up making tert-butylbenzene, which would be this. So now we have our tert-butyl group, and of course that's an ortho. Remember, an alkyl group is a weak activator, and it's an ortho pair director. So now we're adding an ethyl group, and that's going to go not in the ortho position, since this is so sterically hindered. It's going to go in the para position. So we're taking ethyl chloride and aluminum chloride, and we end up with para-ethyl, right? Oops. We end up with para-ethyl tert-butylbenzene. And the last step is benzylic oxidation, right? So this is a two-step process. This is benzylic oxidation, where we convert a benzylic position into a carboxylic acid. But remember, you've got to have an alpha proton, or a benzylic proton to do that. And here there are no alpha protons, and so we can't oxidize that side. And so after steps 1 and 2, so 1 is KMnO4, right? Sodium hydroxide, water. And then in the second step, we treat that with aqueous acid. And what we would end up with then is where we have the alpha proton, we would have a carboxylic acid. And then over here, we would have the tert-butyl group. There we go. All right, so a lot of Friedel-Crafts on the first page. So let's move on from there. The next one is in a similar vein, more Friedel-Crafts. It says, predict the major product of the following reaction and provide a stepwise curved arrow mechanism for the formation of the product. So we have our alkyl halide, we have our Lewis acid. So the first thing is going to be the reaction between our alkyl halide, and this is actually what we call an allyl chloride is what it would be called. But anyhow, that's neither here nor there. So that's going to react with the aluminum chloride. So we're going to dump those electrons in there. And then what are we going to end up with? Something that looks like this, where we have a chlorine with a positive charge and our aluminum with a negative charge. And so this is going to break apart like that. And that would give us a primary but resonance stabilized carbocation. So we go from primary allylic, so primary allylic, and then that's going to be in resonance with something that's even more stable. So once we draw the resonance structure here, we end up with something that's tertiary allylic, right? So now we have a more stable carbocation. And so now our aromatic ring, I'm just going to put that in here. Here's our benzene ring. That's going to react as a nucleophile. So we'll draw the curved arrow like this. And that's going to give us our sigma complex, which is going to look, like this, where we have our positive charge here. Then we have our two methyl groups. There we go. That looks something like that anyway. And then of course, this is our sigma complex. So sigma complex. I'm not going to draw all of the resonance contributors right now, but you should be able to draw each one of the resonance contributors. Okay. And then in the very last step, what's going to happen is that aluminum tetrachloride ion, so the AlCl4, right? That's going to grab this proton. So we have a proton here, which we have to remove in order to restore, sorry, I put it in the wrong spot. My mistake. There we go. I think I need another coffee. There we go. So we're going to pull off that proton. And so what we're going to do is we're going to take the proton like this, restore the aromatic ring like that. And so that gives us our final product, which is going to be this. I'm just going to tilt it over here so it'll fit on the page. And then, of course, we end up with the AlCl3 regenerated, and we also produce HCl at the same time. All right, so that's a mechanism that you should be able to draw, and you should be able to draw all three resonance contributors to the sigma complex. That didn't work very well, did it? So if I circle that, no, that still doesn't work. Anyhow, you should be able to draw those. So let's just practice here. We draw our aromatic ring. There's our positive charge. There's our CHEM dimethyl, right? And so the sigma complex has 3 contributors. So you should be able to draw each one of them. So we have a second one like this. There we go. And then we have a third one like this. And there you have it. Those are all of the resonance contributors for the sigma complex. So there you go. All right. There you go. That's the full mechanism for that reaction. And of course, there's your final product. The next one, hopefully we can avoid some rearrangements this time, because now we're doing a Friedel-Crafts acylation, right? We're starting with an acid chloride. This is going to be a Friedel-Crafts acylation. All right. And so after the first step, we're going to take our aromatic ring and treat it with, so 1, 2, 3, 4. So 1, 2, 3, 4. So this is called butanoyl chloride. The name is not important. We'll learn that later on. So we end up doing the acylation. Remember, with acylations, the beautiful thing is that there's no rearrangements. So we have 1, 2, 3, 4. Then we have the Clemmensen reaction. This is the Clemmensen reduction. Clemmensen reduction, where we use the zinc mercury amalgam. And what that does is it completely removes this part of the molecule. So I'm gonna have to copy and paste this. So let me see here. So we'll do copy, paste this guy over here. There we go. Something like that. Oops. Let me, oh, okay. Yeah, okay. Can you give me like 2 minutes to come up there? Okay. All right, and so the Clemmensen reduction, so with our zinc, mercury, amalgam, and HCl, there we go. And what that does is it removes the carbonyl completely, so you end up with butyl benzene in this case.